Clearly not a single player in the game, one could guess. So let's look at it in two dimensions. And if we just look at it, no, the fact that we have data like this means we can look at it and learn something. One is we have clean isobestic points, which means immediately that there's no more than two species. One is changing to another and they're pivoting around each other. All right, so we know that already. Good. Secondly, we know that if we were to do the, as I've said before, if we were to do the kinetics, first question is, which wavelength do you want? Or, or said a better way, the very fact that the kinetics changes so dramatically, goes change sign, etc., turns to zero at certain points, suggests to anybody with half a brain that if we use all the wavelengths, we're going to get a better answer. All right. How many players in the game? The isobestic point suggests there's at least two. There are two, not at least. So let's ask it. Let's do SVD. Now, trace a shape. Time trace another shape. Flat lines, maybe a bit of noise, no shapes. Unequivocally, the computer says, like you, an observant human, there are two players in the game, A and B. I concur that there are A and B. Therefore, we have a range of more potential fits because we got two things, A and B. Now, the most likely thing, or not likely, one possibility is now, let me say, what we've just done is we're going to be able to get better kinetics because we have multiple wavelength data. Good. The other thing that this stratagem helps with is the computer will draw for us the spectra of A and B, depending, according to the mechanism we propose in the test. So, when I go here, A and B, this says A goes to B with an exponential. All I'm really doing now is getting a better fit on the kinetics because I have all those wavelengths which come and go and so forth. So let's fit them. Good. Now, so here we have the fit. We have A in red, according to this, because I used that mechanism, and A disappeared. Good. And something appeared in its stead, in its place, B, and that's in blue. Now, number one, we got better kinetics, standard deviation, because we did this. Number two, we were told what A and B will look like if the mechanism that happened was A changing to B. Well, we don't know that for sure, but A disappearing, B appearing, all being positive, not being funky in any way, suggests very strongly that what did happen was A changed to B. Therefore, that may well be the right mechanism. But we don't know that for sure. So let's go back to the eigenvectors and say, well, we got two. What about this guy? Here we have A disappearing to nothing, like the DCIP moments ago, and in the test tube, in the reaction, there happened to be some B that didn't change. We have A and B, and we have one rate. Is this what happened? Well, when I select that and say fit it, the numbers for the kinetics are identical, right out to as many decimals as you want, because the kinetics has nothing to do with wavelength. However, notice what it showed us for A and B. This is A and this is B. They look awfully funny, mirror images, but most importantly, A is quite negative. Well, no such things exist as negative absorbance spectrum. Therefore, this is impossible. This is not what happened in the test tube. It didn't affect the kinetics, these are all the same, but that's not the mechanism. So if I go back again and say I've got two species, clearly, I can't argue that. Well, what about this? Well, that's the only one that might fit. The rest are two rates. Well, here's one. A appeared and B was background. That's A and B and one rate. Is that what happened? Now, the kinetics are identical because they have nothing to do with the shapes of the spectrum. However, the spectrum is here strange, and notice the y-axis. It's 1,000. Well, you don't get absorbances of 1,000. They don't go more than 3 or something. So clearly, this is not what happened. And indeed, the only one that makes any sense on this page is A goes to B. Now,